Okay, so let's talk about architecture recovery and consistency. We've sort of adopted this image of the dancing house as our project logo. It's sort of to reflect that maybe the architect has thought, or the architecture has thought, isn't the same as the architecture is implemented. And that's a core concern of our ARC project. You'll notice that we've lots of industrial sponsors: IBM, Phineas, Information Mosaic, QAD, Fidelity, and Munich Re. We've worked with all of these at one stage or another on this architecture recovery and consistency agenda. Before we get into the actual research work we're doing, I just want to talk for a second about the research approach we use, which is called action research. Action research traditionally referred to this process where participants would try to improve their practice. They do this by sitting back and reflecting on what they were doing, what was going wrong for them, the problems they faced, to see if they could reflect and come up with proposals that might improve practice. Once they come up with proposals, they debate and discuss them over and over, typically with someone acting as devil's advocate to try and wreck those proposals. And then the ones that persisted were implemented and tried out in practice and evaluated. And based on this evaluation, it was decided whether they were persisted or whether they were cast aside. And you have this idea of iteration creeping in there, where that evaluation leads to some proposals staying, but also new proposals maybe arising, or some proposals being altered, leading to improved practice over the iterations. We try to carry out our research like that. Obviously, we're not strictly software engineering participants, but we do try to embed our PhD students or our postdocs in the companies so that they become more fully integrated, so that they see the problems, they see the practice, they talk to practitioners, they see how experts address these issues. And they come away with a wealth of field knowledge, I suppose, which they can then combine with what the literature says. This is a good basis for reflecting and coming up with proposals and discussing and debating those proposals as a team, performing that devil's advocate role we talked about earlier, to come up with a refined set of proposals or approaches that we typically embody in a prototype tool. Once we've got this prototype tool, we can evaluate the new approach, typically in vivo, with the prototype tool and see how it worked out. And that's the basis then for iterating, improving, refining over maybe several iterations. So moving on to the ARC project itself, architecture recovery and consistency. Initially in the lifespan of a project, an architect may come up with an architecture for the software system. That is a macro structure for the system made up of components and the relationships between them. So here's one typical architecture where the architect decides to break the system into three parts: the GUI, the business logic, and the database. So the front end, the business logic, and the information store, access to the information store. The architect may decide that there's only very limited connectivity between the GUI and the business. There's a very small interface. And likewise, there's a very small interface between the business and the database. So someone asks for information here, the business logic manipulates what's in the database to return the information back up to the GUI to them. But there's only a very small connectivity, or tight connectivity, bottleneck of connectivity between the GUI and the business and the database. Why might they decide that? Well, they might think, well, the database is small, we might need to replace that at a time. If there's only a few calls from the business to the database, then that'll be easier to replace. If we know exactly what those calls are, we'll be able to just redirect them to the new database. Likewise, you might want a new GUI moving from a PC to a tablet, for example. So if that's the case, we again know what calls that GUI has to make on the business component. So this is a good architecture for, say, evolution. Then the developers come to implement the software system, write the individual pieces of code that make up these three parts. Of course, they're dealing with minutiae, detailed lines of code, not the overview. So it can be hard to remember to adhere to the tight or small interface between these three systems, and maybe they add connections straight from the GUI to the database, for example, against the architect's express wishes. That makes replacing the database harder, for example. Alternatively, they may be under time pressures, or they may actually see a better way of doing things. They may say, well, this takes too long, let's shortcut it and go this way because we have performance issues. So the implemented architecture is slightly different to the envisaged architecture. What we want to do is to stop the inconsistencies between the envisaged architecture and the actual architecture so that everyone's aware of the problem, and so that we move to a consistent architecture. The envisaged architecture becomes the implemented architecture. So reflection modeling, as proposed by Gail Murphy, is a good way of doing this. Here the architect creates a nodes and edges type diagram with macro structures A, B and C, and the dependencies that they think should exist between A, B and C. The system can then be parsed, and the elements, maybe the methods or the classes, can be identified, and the dependencies between those different classes can be identified. Then the architect can map these elements to the macro components. So maybe these ones get mapped to A, these ones get mapped to B, and these ones get mapped to C. And when he does that, you end up with something like this. But as well as the envisaged relationships, you can also see the actual relationships from the pars. What methods or what classes call what classes. So you might see that the envisaged relationships are not exactly the same as the implemented relationships, represented here by dots and dashed lines. So for example, you don't expect C to call A, but actually a class in C does call a class in A. So that's the problem. And those are typically moments of surprise, and the programmer typically clicks on those edges to find out what is exactly happening. So our initial question was, does this architectural awareness increase architectural consistency? Does it make people change either their model, the source code, or the mapping to increase the architectural consistency? Pre-Lero 2, this was supported by a series of Enterprise Ireland Innovation Partnership Awards with QAD. IBM also gave me a Visiting Scholarship Award for 5 years, which was very useful because not only did it give me some money to do the research, but it also gave me the opportunity to access all their programmers up in IBM Dublin, so that was very helpful. And the first SFI Lero Award gave some money towards the support of a PhD student. We had a very prototype reflection modeling tool courtesy of Gail Murphy, and we carried out architectural consistency studies at QAD and IBM. Typically in IBM we focused on the learning management systems and the Domino application portlet system. Just to prove we did, here's an actual reflection model we obtained from the DAPS Domino application portlet system at IBM. You can see the solid lines are as expected, but there are a number of dashed lines where there are relationships that weren't expected, and the tool allowed the developer to click on those dashed lines and see what in portlet was calling what in authentication manager, for example. We got a lot of nice quotes from the people who used it. This is great crack. So they actually enjoyed using it. Surprise led to focus, led to exploration. So there's one that's interesting. Let's have a look and see what that is, what that divergent is. One of probably the best findings we had was up in IBM. One of the programmers we were working with wanted to separate the GUI from the rest of the system because he wanted to change the GUI. I did try the same job 2 months ago and gave up after 2 weeks. This time, including refactoring, it took 3.5 hours. Basically, I have what I always wanted. The LMS doesn't even know the web component exists. And the manager, the architect associated with the LMS project, looked at it and said, "There's not a lot to say. That's right." So that was nice. But an interesting finding was that even in an architectural degradation prompted re-implementation, we did not prompt resolution of violations. So this awareness did not prompt resolution of the violations, even when they were re-implementing a system where architectural degeneration had caused the re-implementation. This was kind of a surprising finding, so we interviewed the participants at IBM to see why. Sometimes violations just had to be, there was a legacy component they didn't want to touch, so they worked around it. Sometimes they were considered small architectural violations, not really important enough to address. But in terms of the bigger ones, they said, well, refactoring can cause ripple effects, and those ripple effects can change the structure of the program a good bit and can meddle with the programmer's mental models. So now the programmer doesn't know where to go when they're looking for something. Also, they said that, okay, it's easy to apply one refactoring, but that one refactoring could change something else, which actually makes the architecture worse. So we'd like ideally a suite of refactorings and a sequence of refactorings applied that would allow us to decrease the overall violations, but that's not as easy a task. In summary, they didn't want the effort to change after the fact, and it was hard to do. So that suggested to us that we give them real-time tooling, and we look into an analysis of sequence of refactoring applications. The real-time tooling is called JITTAC, Just-in-Time Tool for Architectural Consistency, and you can see a demo of it at this location. In fact, it's available on the Tools tab on this website, and you can also download and play with it yourself on the Tools tab. Just to give you a quick overview, here's the model that the architect makes. You can create nodes and edges between them, and then he can drag things from the Package Explorer to each of those nodes and see if they're consistent edges or if they're inconsistent edges with this model. We subsequently carried out 4 empirical studies with JITTAC, well actually 5 systems, 4 financial services companies ranging from 45,000 lines of code to 2 million lines of code systems. The findings, they had typical uses, so people looked at bypassing APIs. So when an API was bypassed, they didn't like that, and that was something that reflection modeling allowed them to do. They also had envisaged their system as a layered model, so there were the 2 types of models we got: the adhering to APIs or the layered model. Scalability was an issue. As models got larger, it got harder to see the wood for the trees. The graphs became very, very dense. But scalability was also another issue in that they desired to move beyond the source code analysis. So we're looking at Java source code and the dependencies in Java source code. Modern systems are made up of lots of different languages, descriptors, XML, so they wanted to, and components that you don't have the source code to indeed. So they wanted to move to larger scale architecture, I guess. Surprising to us was this idea that they wanted a feature-orientated perspective, a functional-orientated perspective of a macro structuring of the system. Software architecture typically concentrates on non-function perspectives, maintenance perspectives, performance perspectives, but not the functionality of the system perspective. So that was a bit of a surprise. Just the people we tried it out with wanted a feature-orientated perspective. And of course the finding that less than 50% of our violations identified were removed 4 months after the original reflection modeling sessions. So I suppose if I was trying to characterize the key impacts of the project, one of them is that identifying violations did not typically result in their removal. A lot of effort has gone into this field, but most of it has gone into identifying violations. No one has really followed up to see if those identifications typically resulted in their removal. Another surprising finding was that there was a keen interest in a functional perspective at the architectural level, a functional view of the system at the macrostructure level. That was interesting to us. We've had publications in leading journals and conferences, ICSI, SANER, SCAM, Quality of Software Architecture, journals IST and SPE. We've obtained funding. I got an SFI Principal Investigator Award in Architectural Recovery. This functional perspective led to collaborations with a company and a Lero project, a Lero 3 project worth 600,000, and an Enterprise Ireland Innovation Partnership project in feature location. We brought one of the leading conferences in architecture recovery, software re-engineering, WCRE to Ireland in 2011. We've been running a software architecture erosion consistency workshop and industrial seminars over the last 3 to 4 years, and Sirocon is now beginning to get critical mass where it could be something that perpetuates. We have 2 PhD students graduated and 3 in progress. Possibly the thing I'm most proud of is the quality of JITTAC. It's been used on systems 2.2 million lines of code long, so it's fairly robust. But also in Leo Pruschit's article on software practice and experience in 2006, where he compared JITTAC to 9 other architectural conformance tools, 4 of which were commercial offerings, JITTAC was best in terms of dependency identification, so it was probably the most accurate architectural consistency tool. You can see it has the highest number of stars here. Also, in Pass's review of the area, he said that our approach was best for organizations interested in systematically incorporating architecture conformance checking into their software development process. So that was a nice reflection of our work. So where does this lead us? Well, we got more and more interest in this feature location problem. I'll talk about that more under the FOSSMO part of the project. Indeed, companies have come to us with related dilemmas to this feature location problem, so that's led to the FOSSMO project, and I'll talk about where that led us in a few minutes, but specifically it led us to the Flints and Fusics approaches. See you then.